Chapter 8, Thermochemistry and Chemical Energy. So first, let's discuss the different types of energy. Kinetic energy is the energy of motion. Potential energy is the energy of position. Thermal energy is the energy of random motion that we see in molecules. So thermal energy and kinetic energy are directly related. Chemical energy would be the energy that's stored in bonds, specifically covalent bonds. And electrostatic energy is the energy of attraction between positively charged particles and negatively charged particles. So electrostatic energy is also a bond energy. And looking at potential energy and chemical energy, we can look at the energy stored in bonds. So if you break a chemical bond, you are able to release that energy. That energy is being stored. It's potential energy. So a couple more things here. Heat. Heat is actually a transfer of thermal energy between two different objects that are at different temperatures. So heat is a transfer of energy. When we look at thermochemistry, we're actually studying the heat, the thermal energy that is associated with chemical reactions. Now, it's important to realize that heat is not the same thing as temperature. Temperature is actually measuring the amount of thermal energy, which that energy comes from the energy of motion in those particles, in the molecules that are present. Heat, once again, is measuring a transfer of energy from a hotter object to a cooler object. We also can discuss here the difference between a system and the surroundings. So the system is what you are studying. So we're going to isolate something away and say, this is what we're going to study. We are going to study the energy associated with melting an ice cube. That would be our system. The surroundings then is everything else. The whole universe can be the surroundings. So we can look at the difference in energies between our system and our surroundings. And the entire universe is made up of systems and surroundings. So types of systems, we have an open system, which means that both mass and heat can be exchanged with the environment. We have a closed system where no mass can be exchanged, but heat can be exchanged. And then finally, we have an isolated system. So here we have an insulated bottle, so no water can escape or come in, so there's no exchange of mass. And because it's insulated, there's no exchange of heat. So we studied before the law of conservation of mass. It's very similar to the first law of thermodynamics, which basically states that energy cannot be created or destroyed. So the energy of the system, delta E, this is a change in the internal energy of the system, plus the change in the internal energy of the surroundings will always equal 0, which basically means that if the energy of the system is being transferred potentially to the energy of the surroundings. So these values are equal but opposite in sign. If I gained 100 joules of energy, it had to come from somewhere. So that 100 joules, it either belongs to somebody else or it belongs to me. But we cannot create or destroy energy. So here we have an example of burning a Bunsen burner, which has propane gas. And the heat that is given off by this blue flame here then is absorbed by the surroundings. So what is thermodynamics exactly? Thermo means we're going to study thermal energy. We're studying energy changes. And dynamics means change. So change in energy associated with different processes. It's also important to define whether something is a state function or not. And if we look at these two hikers, they both started at the same point, but they took different paths. So a state function is something that is path independent, doesn't matter. So here, distance traveled by the two hikers would not be a state function because clearly they are different. They are path dependent. This guy took a shorter route, this guy took a longer route. Now, a state function that is associated with this would be the elevation difference. They both started at the same point. They both ended at the same point. So that change in elevation would be considered a state function because it does not matter on the path that was taken. Anytime that we can put a delta sign in front of something, that means that it is a state function, which effectively means that it only depends on what the initial state was and the final state. So what was our initial energy? What was our final energy? Here, big capital P stands for pressure. What was our initial pressure? What was our final pressure? Big V here, volume, initial volume, final volume. Big T for temperature, initial temperature, final temperature. So anytime you can put a delta sign, a triangle in front of a symbol, it means that it is a state function. So it's interesting to note that a state function here in the change of internal energy is dependent on two functions that are not state functions. Q represents heat, W represents work. So once again, delta E is a measurement of the internal energy of the system. And really this comes from the thermal energy. It's kinetic energy, also potential energy. So once again, Q stands for heat. It is a path dependent as well as work. Work is a path dependent function. And you can think about this too in terms of if you've ever had to move something, depending upon if you have assistance with it, how difficult is it? How much energy do you have to put in? If I have one of those little Caterpillar trucks, well, it's not really a truck, tractor, whatever you want to call it, a forklift, right? To lift up something really heavy, that's doing the work for me. Versus if I had to do that, I would have to expend a lot more energy. So in chemistry, we actually look at work in terms of pressure volume changes. So we're looking at the expansion or contraction of a gas. So we call this PV work. Now, depending upon what the signs are for Q and W, will indicate what the overall change is then in the internal energy of the system. If they're both negative, meaning heat is given off, and work is being done by the system on the surroundings, the delta E is going to be negative. If Q is negative, which once again means that heat is being transferred from the system to the surroundings, but work is positive, which means the surroundings is doing work on the system, it depends on which two of these is higher in magnitude, right? A negative plus a positive, it depends on the magnitude. And we can look at it conversely. If Q is positive, it means that energy is being gained, thermal energy is being gained from the surroundings to the system. So we're gaining internal energy in that example. If work is negative, that means that the system was doing work on the surroundings. So it's effectively losing energy. So we're once again in a system where we have a positive sign here, a negative sign here. So it depends on the magnitudes of those to see what delta E would equal. Your last situation would be if both Q and W were positive. That means that overall heat is being absorbed from the surroundings into the system and work is being done from the surroundings onto the system. So we have 4 different scenarios here that are going to determine, are we increasing our internal energy of our system or are we decreasing the internal energy of the system? So work, by definition, is a force applied through a distance, so force times distance. And like I say, with chemistry, we're looking at expansion, gas expansion or contraction. So we can look at an initial set of conditions here. We have pressure coming from the atmosphere. We have a specific volume of gas in this container. And if the gas is going to expand, that means that it has to push against whatever pressure is here. So we see a change in volume. Work had to be done by the system onto the surroundings in order to expand. Conversely, if we were going to compress the gas, then the surroundings would have to be doing the work because they would have to push down on the gas to make it be in a smaller amount of space. And you do not have to worry about this conversion. It just shows how we can show that PV work is really work. Excuse me. So 2 different types of heat exchanges that can happen, exothermic versus endothermic. And exothermic, exo meaning it is going to be given off. So heat is given off in an exothermic process from the system to the surroundings. And anytime we see an exothermic process, it is going to have a negative sign associated with that energy. So endothermic means coming into, inside. So we're gaining energy from the surroundings into the system. Endothermic processes have a positive sign associated with it. So anytime you are absorbing energy, you are gaining the energy, that energy is positive. If you are giving off energy, you are losing it, therefore it is negative. So here are our 2 systems, or here are our 2 examples. System giving heat to the surroundings giving heat to the system, but either way, the universe stays constant. So the energy associated with either of these changes does not affect the total energy that is available in the universe. Both energy and mass are constant. However, we can actually convert mass to energy and convert energy to mass, as Einstein showed us in his famous equation, E equals mc squared. So we have a fancy word here called enthalpy, and enthalpy is just another way to discuss energy transfers, heat transfers, basically. So if I look at the internal energy equation, delta E equals Q plus W, and I keep things at constant pressure. So this remains constant. This here, Q sub P, means heat at a constant pressure. What is happening there with this transfer of energy under constant pressure? When we have that, we set that equal to delta H, where H stands for our enthalpy. So enthalpy, by definition, is a heat transfer that occurs under constant pressure. We can plug these into our delta E equation and see, and do a little rearranging here, and see that the enthalpy change depends upon both the internal energy change of the system plus the work that is done, our PV work. If instead we do our energy studies at constant volume, which is called isochoric, now we have Q sub V equals our heat. Work is still a negative P delta V. We can plug that into an equation, but if we are at constant volume, that means this is 0. So P times 0 is 0, which means there is no work that can be done at a constant volume. So our delta E simply equals Q, which is our heat. So 2 completely different scenarios here. And we are actually going to be doing an experiment where we are under constant pressure. So some more things here about heat. We have specific heat, and the specific heat of an object is the amount of energy that is required to raise 1 gram of a substance by 1 degree Celsius. You can also see specific heats listed in terms of the amount of heat per 1 gram of substance per degree Kelvin, or not degree Kelvin, per Kelvin, because the degree Celsius and the Kelvin temperature scale both change in the same increments. So if I look over here, I have specific heats listed. Notice I have a very large specific heat for water. That's very important. It takes a lot of energy to actually change the temperature of water. So doing a little thinking here about what this chart means, if I compare copper to aluminum, copper's specific heat is 0.385. Aluminum has a specific heat of 0.900, which means that it's going to take more energy to raise aluminum's temperature than what it would for copper if I have the same amount of mass of both of these substances. And this is important in terms of different types of pans that we use. There are copper skillets, there are cast iron skillets. So we can look at this and see, oh, okay, if I compare copper and iron, well, my copper pan will heat up faster, but my iron pan would hold the heat longer. It would actually take longer for it to cool down. So specific heat, once again, the amount of energy, which is represented in joules, that it takes to change 1 gram of a substance by 1 degree Celsius. Now the heat capacity actually takes the grams out of it. So now we can just look at what is the heat capacity of this object. So it really comes from the specific heat where we've already multiplied by the mass. And interestingly enough, you can have a higher heat capacity in a cooler substance. So let's say we had a bathtub full of ice water. We can actually have more heat present in that than a cup of hot coffee. It's just a bigger body. There's more heat associated with it. So we can look at two different equations here. Heat absorbed or released. So once again, Q is our heat, equals the mass of the object, times S, which is the specific heat, times the change in temperature. So we're looking at what is the heat associated with a temperature change, which that is by definition what heat is. We can also look at heat in terms of the heat capacity of a substance times the temperature change as well. We are going to be using this equation within our studies. And once again, our delta T is the temperature, our final temperature minus our initial temperature. So it's always going to be final minus initial. So two different types of calorimetry that we can do. And a calorimetry experiment is really just being able to measure heat, being able to measure those energy changes for a chemical process. So that's calorimetry. So what do we have set up over here is a simple calorimeter where we have two styrofoam cups, and this is the experiment that we're going to do. We have water in here, most likely, and then we can add in some type of substance, either another liquid or a solid, and effectively we are measuring an initial temperature, and then we have done our reaction, we stir it up, and then we measure our final temperature. And we will be able to then determine the heat that is associated with a chemical reaction. So the way that we do this, we have our system defined, which is simply this cup. This is our system. So what is part of our system here? The water that is in the cup, the calorimeter itself, which is QCal, and the energy that's associated with the reaction that will take place in here. So all of this affects the heat of our system. So the heat of our system has to be 0. Why? Because the energy that is gained by the water or lost by the water is the same amount of energy that is either lost or gained from the reaction itself. And really we can look at the water and the calorimeter as being our absorbing things together effectively. So Q of our reaction equals the negative of the heat that is associated with both the water and the calorimeter. Effectively, it's almost like looking at our water and our calorimeter as our surroundings in this system. So we can measure the change in temperature of the water. That's really simple to do because we have a thermometer here. So we can measure our change in temperature. The specific heat of water is given in a table, and we can take the mass of the water. Generally speaking, the calorimetry constants are given as well. So we have a specific heat or heat capacity for our calorimeter, and that will change by a specific amount based on the temperature difference. So we can add those two things up, Q water plus Q cal, and then change the sign. And the reason why we change the sign is because this is following the first law of thermodynamics, which says that the heat that is lost or gained by the reaction has to equal the heat that is gained or lost by our water and calorimeter. So this negative sign just allows us to show that one of these is giving off the energy, which would be exothermic. One of these is gaining the energy, which would be endothermic. So hopefully this makes sense. If the water temperature is going to increase, if we're starting at a lower temperature, ending at a higher temperature, that means that the water had to gain energy. Where did it gain the energy from? Well, it had to come from the reaction. So the amount of energy that the reaction is losing would be gained by the water. Now, if instead of seeing a temperature increase, we see a temperature decrease, that means actually that the water was losing energy. Where was it going? Into this reaction. So when we study constant pressure calorimetry, the Q of our reaction is equal to our enthalpy, our delta H. We can also do constant volume calorimetry, and these are also called bomb calorimeters because we are actually combusting a compound within a sealed vessel, and we will see that there's going to be a great pressure increase. However, we are not changing the volume because it is sealed off. In the previous slide, the reaction mixture was under constant pressure because it was simply open to the environment, and the pressure around us is not changing by very much anyways. So once again, we have the heat of the system equals heat of water plus the heat of the bomb calorimeter plus the heat of the reaction. Q of the system has to equal 0, which means that our Q of a reaction equals, once again, the negative Q of our water and the Q of our bomb. So this, once again, tells us that the heat lost has to equal the heat gained, or vice versa. So we're going to measure our heat by seeing what the temperature change is. Mass of the water times the specific heat of the water times the temperature change. Same thing here. We have a heat capacity constant for our calorimeter times the temperature change. Add these two things together and it gives you the Q of your reaction. Now, because we are not under constant pressure, we are not actually measuring an enthalpy change for this. We're really just measuring an internal energy change. But we can say that it's approximate. Because we're not doing work, it is an approximation that, yes, Q of your reaction is almost equal to our enthalpy change. So some rules for studying thermochemical equations. First of all, these values will be listed in the back of your textbook in an appendix, which means once we start this chapter, you need to make sure that you have that part of the book with you at all times, as well as your calculator. So if I look here, I have water as a solid going into water as a liquid. If I'm going from solid to liquid, it means that I'm melting. If I'm going to melt, it means that I have to gain energy from the surroundings. That is shown here because we have a positive value, 6.01 kilojoules per mole. So what happens then if I reverse the reaction? Well, anytime you reverse a reaction, you reverse the sign of whatever the enthalpy change is. So instead, liquid to solid, that means that I'm freezing. This is a freezing process, which means that I have to get cooler, so I'm giving off energy. But notice the magnitude does not change. If within a chemical equation, I'm multiplying through by a coefficient, whatever my coefficient is here, it's 2, means that I multiply my enthalpy change by 2. So once again, we have the same equation as what's given above. And the importance of this that I wanted to point out here is that we have to pay attention to our states of matter. So we can't just write H2O goes to H2O, because what states of matter are we in? Here, going from a liquid to a gas, that's an evaporation process. And it takes a lot more energy to change something from a liquid to a gas than what it does a solid to a liquid. So we have to pay attention to our states of matter because we're going to do thermochemical equations, and we have to make sure that we have the right values for what we are trying to calculate. So standard enthalpy of formation, standard state, that's where that comes from. And the standard state for thermochemistry is when we have things at 25 degrees Celsius, which is the same thing as 298 Kelvin, and we're under 1 atmosphere of pressure. And if we are looking at an aqueous solution, then we have 1 molar concentration of this solution. So this is our standard state. Room temperature, which we've assigned effectively is 25 degrees Celsius, where all reactions are effectively taking place. Under atmospheric pressure, which is usually about 1, and our standard solution concentration of 1 molar. So here's our standard state. Enthalpy means heat transfer under constant pressure. Formation means elements coming together to form a specific compound. So this is how we represent this. The change in enthalpy of formation under our standard state. So we call this little 0 at the top here. It's not a degrees symbol. We actually call this naught. So delta HF naught, standard enthalpy of formation. So I discussed the standard state for elements. If you had to take a guess, what is the enthalpy of formation for an element? Any element. It's 0 because you are not forming elements. Elements are already existing. So standard enthalpies of formation look at what happens, what is the energy change for when we take our elements and we form, hence formation, a new compound. So for example, I have some things listed here of their standard enthalpies of formation. So O2, diatomic oxygen, it's in an elemental state, so it has an energy of 0. Here we have ozone, not an elemental state. Ozone was formed from oxygen molecules, so we have an enthalpy of formation. Here we have two different states of carbon, and when it's graphite, that is the simplest or most stable form, so it is given an enthalpy of 0. But when we form diamond, under enough pressure with enough heat, we can change graphite to diamond, so we see an enthalpy of formation for that substance. And once again, we have to pay attention to what the states are for these things. Liquid oxygen, as opposed to gaseous oxygen, would actually have some enthalpy associated with it because it would not be under its standard state. This is looking at how things exist in our everyday world. If it exists in a specific form, then it has no enthalpy of formation, like elements. Okay, so how can we use standard enthalpies of formation to actually figure out what our enthalpy changes are for reactions? So these are pen and paper calculations. We're not going to do an experiment with this. We're going to actually reference our tables. So once again, standard state, 25 degrees Celsius, 1 atmosphere of pressure. Enthalpy, change in energy, change in heat under constant pressure of our reaction now. So we have a delta H reaction naught. And the way that we're going to do this, if we look at a generic equation here, my little letters are representing my coefficients. My big letters are representing my specific compounds. So do not be intimidated by this equation. All this is telling me is I'm going to look at the total enthalpy of my products, and then I'm going to subtract out the total enthalpy of my reactants. Right? C and D are my products. Little c here says if I have so many moles of this, well, if I have 3 moles of compound C, then I have to multiply my energy by 3 because I have 3 times the amount of it. So you do this same calculation for each of the substances that you have present in your chemical reaction equation. Where do these values come from? They are not memorized. They are given to you in the appendix of your book, Standard Enthalpies of Formation. So you're just going to copy these down and then look at multiplying by whatever molar coefficient is present. So we can simplify this. Anytime you see this big capital symbol here, that is sigma, is that sigma? Maybe it's epsilon. So we have an epsilon here, which means take the sum of, that's why I was thinking sigma, because I wanted to say sum. So I have number of moles times whatever my enthalpies are for all of my products. This means I take the sum of them, and then I subtract the sum, which means add it up, of all the energies of my reactants. And really what this looks at is how much energy is given off when we're forming new compounds, because energy is going to be given off when we form new bonds. Atoms are floating around. If they're not hooked up to anybody, they come together, they become more stable, energy is given off. Now, on this side of the equation, we actually have to put energy in to break these bonds. So this energy is going to be positive, this energy will be negative, and then we can look at the difference between these two things. Hess's Law. So Hess's Law allows us to do thermochemical calculations in a stepwise fashion. So what really Hess tells us is that the enthalpy change for reaction is going to be equal to, or it will be the same regardless of the number of steps that you took. Is it a one-step process, or did you go and do 3 different steps? Regardless, your enthalpy change is the same. So if I look here, I have a reaction that's happening here. Let me get the rest of this up. So my overall reaction is carbon is graphite, that's its elemental form, plus oxygen in its elemental form, comes together to form carbon dioxide. So I can do this in one step, C graphite plus O2 gas, to get to CO2, or I can do it in a series of steps. I can take graphite, react it with oxygen to give me carbon monoxide and half of an oxygen molecule. That's what we're showing here. Then I can take my CO plus my 1/2 oxygen and form carbon dioxide. So that's the step that we're showing here. So regardless, I have a negative 110.5 kilojoules to do this reaction, carbon graphite plus oxygen to give me carbon monoxide. I can then take my carbon monoxide, react it with my half of an oxygen molecule. That energy is negative 283 kilojoules to form my carbon dioxide. I can add these two values together and it's going to equal this value. So Hess's law, once again, it comes from the fact that enthalpy changes are state functions. It does not matter on the path. It is simply where you start and where you finish. Well, we're starting at this point, we're finishing at this point. So it doesn't matter the steps that we take in between, whether it's one step or a series of steps. And we'll find that we can manipulate equations and use enthalpies of reactions to actually calculate an enthalpy change for a given reaction without having to do any experimental work. So another way to look at enthalpy changes for a reaction is to study or to look at bond enthalpies, and that's simply the energy in a bond, in a chemical bond. So we have a bunch of bond enthalpies listed here. These are for covalence because here I see I only have nonmetals. And our equation has changed a little bit. When we were looking at studying standard enthalpies of formation, it was products minus reactants. Now we have the enthalpy associated with our bond energies of our reactants minus the bond enthalpies of our products. So once again, this energy has to be put in, so it is positive. This energy is going to be given off because I see a negative sign here. So we're looking at the difference. If there's more energy put in than what is released, then we have an endothermic process. If there's more energy released than what was put in, then we have an exothermic process. Either way that you calculate a delta H, whether it's with enthalpies of formations or bond enthalpies, it should come to the same value because it's the same reaction and we're not changing energies based on the way that we calculate the energy. So how can we tell whether something may be product or reactant favored in terms of the energy? If I look here at this system, I have water as a solid, which means it's ice, and it's melting to form a liquid. So when is this product favored? When would we have a liquid? When would we have the solid? Well, it's going to depend because this process requires energy. So if this energy is available, then we would see this happen, right? If we have our solid water in the freezer, this isn't going to happen. It would be reactant favored. But if we take our ice cube tray and set it out on the counter, now we are going to favor the products because of the energy change associated with it. We have the energy necessary. Here I have methane gas combusting to form carbon dioxide and water. So heat is given off. So this is an exothermic process. Generally speaking, exothermic processes are more favored. But in order to do this, in order to burn methane, just because I introduce methane to oxygen doesn't mean anything's going to happen. I actually have to have some sort of spark, right? This is a combustion process, so I have to be able to ignite the fuel. So if I have no spark of energy, this reaction will not happen. I would stay as reactants. But once I get that initial source, that initial heat, then this will form products, and it will continue to form products until we lose out on our fuel, when all the fuel is gone. So product or reactant favored, it is situational. Depending upon what the conditions are, we either are going to favor the products or we're going to favor the reactants. So, and another way to look at this then is to study whether or not we have a spontaneous process. So if it's spontaneous, it means that it will occur. A spontaneous process occurs without any type of intervention, without any help. So a spontaneous process would be the fact that the leaves are going to fall off the tree in the fall. Nobody makes the leaves fall off. They fall off on their own, right? There are chemical processes that are happening in order for the leaves to fall off the tree, but inevitably, the tree loses its leaves. Now, the leaves fall to the ground. Why? Because gravity's acting on it. So a spontaneous process is if you drop something, it falls to the ground. We don't push it to the ground. It just happens. Same thing with any type of food. Any type of decay process is always going to be spontaneous. The fact that milk will sour, right? It sours less quickly when you keep it in the refrigerator than if you were to leave it out on the countertop. So a spontaneous process is something that occurs without outside intervention. So the driving force for a spontaneous process is looking at an increase of entropy in the universe. So what is entropy? Entropy is a study of randomness or disorder or simply the probability of existing states. So nature is always going to tend to move towards the states that have the highest probability of existing. So effectively, the universe tends towards chaos because the more things that there are, the more states that they can exist in, the more randomness then that occurs. So we are increasing entropy. So there is no conservation of entropy. The entropy of the universe is always increasing. So entropy of the system plus entropy of the surroundings should result in an increase in the entropy of the universe. We do not conserve it the way we conserve mass and energy. So looking at entropy and heat effects. Exothermic versus endothermic. And once again, we have to define here. So we're looking at the entropy of the surroundings in this process. So if we have an exothermic process, which means that our system is giving off energy, the surroundings then is gaining the energy. And if we have more energy, we have more thermal energy, it means that our particles are moving faster. Therefore, there's more randomness, so our entropy increases. When we have an endothermic process, that means actually that the surroundings is supplying the energy. So the surroundings is cooling in that process, which means we have less motion of those molecules, so less entropy. So in studying the surroundings, entropy increases in an exothermic process, entropy decreases in an endothermic process. But once again, this is for the surroundings only. So the last bit of thermodynamics, and this once again is just an intro here of entropy and free energy. We'll study that more in chemistry too. So Gibbs free energy, which is why it's given big capital G. Gibbs free energy is looking at both enthalpy and entropy to determine whether or not we are going to have a spontaneous process. Because spontaneity tells us nothing about time. Yes, for example, there are radioactive isotopes. Some of those isotopes take 1 million years to go through one half-life, which means that we have half of our remaining sample left. 1 million years, okay? So the process is spontaneous because it's naturally decaying, but the amount of time that it takes is not reasonable. Okay, so Gibbs free energy, we're only going to look at the system. And we can look at our delta H and our delta S to determine whether or not we have a spontaneous reaction. So when a reaction is spontaneous, that means that delta G has to be less than 0. So we're decreasing the amount of energy. Delta G then it's giving off. It's a negative energy. It's energy that then can be harnessed to do work. So when delta G is greater than 0, which means it's positive, that means we have a non-spontaneous process. When delta G is less than 0, it means it's negative, so we have a spontaneous process. When delta G equals 0, we are at a situation where we have an equilibrium. And I discussed equilibrium briefly in the last chapter when we looked at those back and forth arrows. We're at equilibrium. We have come to a place where we are forming we're forming products at the same rate that we're forming reactants. So there's no free energy associated with that. So once again, we can look at how do the signs of our delta H and delta S affect our delta G. So when we have an exothermic process, that's negative, and this is for the system. We have an exothermic process. We are increasing the entropy of the system. Delta H is negative minus a delta S times the temperature, where that's positive. So negative times a positive is a negative. Negative plus a negative is still negative. So it's spontaneous at all temperatures. Now, when we have an endothermic process, meaning that the system has to have energy, it has to be able to absorb energy from somewhere, but we are increasing the entropy of the system. That process will only be spontaneous at high temperatures. And a good example of this would be anytime we are trying to evaporate something or melt something. And this is because, evaporation and melting. We are absorbing energy, but the randomness of our particles is increasing in either of those situations. Because if I have a solid, all those particles are packed really tightly together. If I've melted them, they become a liquid. So there's all kinds of motion in a liquid. If I take that liquid, I add more energy to form a gas. Now I've got a much higher temperature for that gas, and there's a much higher amount of random motion in a gas than what there is in a liquid. So another situation where the signs are the same, delta H is negative, which means exothermic process, but the entropy of our system is actually decreasing. This is only spontaneous at low temperatures. And so conversely, when I looked here at either melting or evaporating, now we're looking at the opposite. If I'm going to condense a gas into a liquid, energy has to be given off so that I can cool down, and then I become more ordered, which is why there's a decrease in entropy. So this also holds true for when you're trying to freeze something. So a liquid to a solid. I am taking the randomness out of the motion of the molecules in a liquid and making them freeze, making them stay in one single place and compacting them together. But energy has to be given off to do those two processes while the entropy is actually decreasing. This last set of situations is not spontaneous at any temperature, and that is because we both are requiring energy, because enthalpy here shows me it's endothermic, and at the same time we're actually becoming more organized, or the entropy of the system is decreasing. So this process will never be spontaneous. All right, so within this chapter is all about energy changes. We're going to look at studying heat capacities and how that can allow us to calculate heat transfers or enthalpy changes under constant pressure. We will also look at calculating enthalpies of reaction using our appendix that lists our standard enthalpies of formation. We will also apply Hess's Law, and once again, we're going to be looking at enthalpies of reactions now and manipulating those equations in a way such that we can get to our desired equation, because Hess's Law tells us that enthalpy changes do not depend on the path. They are state functions. So 1 step or 5 steps is going to give us the same result. So this is a lot of math. We're not going to do a whole lot of conversions in here, but take a look at the tables. Make sure you understand the differences between heat and temperature, systems, surroundings, work, whether that sign is negative or positive, heat, whether that sign is negative or positive, and how it affects the overall energy changes for our system. All right, good luck studying.